Okay, so thank you so much for the invitation. It's a huge honor for me to be here for Claudio. So today I'm going to talk about, I'll focus on high-dimensional critical percolation, and I'll talk about a new notion that we have introduced in joint work with Amine Asselah, who is in the audience, and with Bruno Schapira, who is not here, he's in Lyon. I'll talk about this new notion of capacity for percolation, but in order to motivate it, I'm also going to talk about the analogous results for critical branching random walks. So let me start the talk by first recalling the model of bond percolation. So bond percolation on ZD. So what is the model? So every edge E of ZD is independently declared to be open with probability P and closed with probability 1 minus P. Oh, sorry. So the only parameter of this model is the parameter P that an edge is open. And now a well-known result, a very classical result in percolation, which goes back to Broadbent and Hammersley, states that if dimension D is greater than or equal to 2, dimension 1 is trivial for this model, is degenerate, then there exists a critical value PC, which depends on dimension, and it's non-trivial in the sense that it's strictly between 0 and 1, so that for all P greater than PC, if I denote by C of 0, the cluster of 0, so I mean all the vertices that are connected to 0 via open paths of edges, then if I define by theta of P to be the probability that this cluster has infinite size, if we are in the supercritical regime, this probability is positive, while if P is less than PC, then theta of P is equal to 0. So above the critical threshold, there is with positive probability 0 is part of an infinite component, and in this case there is a unique infinite cluster on the whole of ZD, and in the subcritical regime all components are finite almost surely. We know what happens above and below criticality, and the question is what happens at criticality. So I mean when P is equal to PC. In particular, is the function theta of P continuous at this at the critical threshold? So is theta of PC equal to 0? So if dimension is equal to 2, then Kesten proved that PC of the two-dimensional lattice is equal to 1/2, and in particular, theta of 1/2 is equal to 0. So there is no infinite cluster at the critical value. But this is really special to the two-dimensional case, and once D becomes greater than or equal to 3, then the question becomes much, much harder, especially when we are in low dimensions. So low dimensions, I mean above 3 and below some dimension, which now has been reduced to 11, and I'll say what happens above. So this is a very hard problem, and it's a huge open question in percolation to prove that theta of PC is equal to 0 in 3 dimensions. So low dimensions are hard, but there has been a lot of progress in high dimensions. So much more is known. in high dimensions. And why is this? So this is due to a very powerful technique which was introduced by Hara and Slade, and later with improvements by Fitzner and van der Hofstad. So this technique is called the lace expansion. And with this powerful technique, now we understand much better dimensions d greater than or equal to 11. So I'm not an expert on the lace expansion, so I'm not going to go into this, but I want to state the results that are known now for dimensions greater than or equal to 11. So initially, Hara and Slade, using the lace expansion, understood dimensions greater than or equal to 19, and then it was pushed down by Fitzner and van der Hofstad to d greater than or equal to 11. So what is the important result that they proved? So let me first introduce some notation. So if we have x and y, two vertices of ZD, then I'm going to denote the event that x and y are connected by an open path of edges by this notation. So I mean that there exists an open path of edges joining x and y. So what is known now is that at criticality, so when p is equal to pc, the probability that x is connected to y is asymptotic to some constant which is depending on dimension, divided by x minus y to the d minus 2, and this asymptotic is valid as long as x minus y goes to infinity. So as long as the 2 points are far apart, then the probability that they're connected decays like the inverse of their distance to the power d minus 2. So this is called the 2-point function. So this was established in these works for dimensions greater than or equal to 11 using lace expansion, but there has been some recent progress by Godin-Copain and Romain Panis, who used different arguments, a more direct approach and a direct comparison with random walk to obtain the same bounds, avoiding the lace expansion. Okay, so that's the outcome of lace expansion. And then using this 2-point asymptotic, about 14 years ago, in 2011, Cosma and Achmias studied the question that 0 is connected to the boundary of the ball of radius r centered at 0, at criticality. So here we have the 2-point function. What is the probability that 2 points are connected when they are far apart? And now we want to know how this probability decays as a function of r. And so in a breakthrough paper, they showed that this is of the order 1 over r squared. And they showed that as long as the 2-point function asymptotic holds. So as I said, this has been proved for dimensions 11 and higher, but it's actually expected to hold for all dimensions d greater than 6. So this result establishes this asymptotic as long as the 2-point function holds, the 2-point asymptotic. And one quick comment, when I write the symbol, I just mean that they're universal constants, so that this is upper bound by 1 constant times 1 over r squared and lower bounded. Yes, Milton?
What is the dimension restriction of the sort of Hugo?
They are not yet down to 6. And I don't think they can get the, maybe they can, but I don't think it's out yet. Okay. So, so what we know so far is the probability that 2 points are connected and the probability that 1 point is connected to the boundary of a ball centered at this point of some large radius. So what I mean with Amine and Bruno, the question that we asked is how can we generalize this function instead of just looking between 2 points or between a point and the boundary of a ball around it, how can we generalize it by replacing 1 point by a set? Or more generally, how can we generalize it if we replace both points by 2 finite sets that are far apart? So let me just fix, so A is going to be a finite subset of ZD. And let's say that it contains 0, so I just place it around 0. So the question is, how does, the probability that X connects to A, so this is again the same notation that there exists an open path that goes from X to some point in A. So how does this function depend on A and X for large X? So that's the question that we were interested in. And so we'd like to understand how this function depends on the set A. And so we'd like to introduce some notion of the size of A, some notion like capacity. So before I say what this function is in the case of percolation, I'm just going to take a step back and go to a model that everybody's familiar with. And this is a simple random walk on ZD. And I'm going to take D greater than or equal to 3 so that the walk is transient. So let me denote the walk by xn, n greater than or equal to 0. Now, because we are in transient dimensions, if we take any 2 points x and y, and we count the total local time at y, so the total number of visits to y for a walk starting from x, we know that this is going to be finite. And this is the Green's function between x and y. And it's well known that this function is asymptotic to some constant which is depending on dimension divided by x to the d minus 2 as x goes to infinity. And this constant is the same constant that appears in the 2-point asymptotic for percolation. So let me, okay, maybe I'll introduce this notation here. So A is always going to be a finite set. So let me denote by HA the first hitting time of A. And I will denote by HA plus the first return time to A. So it's the first time after time 1 that the random walk comes back to A. And the analogous question for the random walk is, what is the probability that the walk starting from X, and I'm going to take X to be far away, ever hits the set A? So this probability is given in terms of what is known as the Newtonian capacity of the set A. And the capacity of the set A, there are many equivalent definitions. So I'm going to give you 2 probabilistic definitions and 1 analytical definition. So what is the capacity? So the first definition is the following. So the capacity of A is defined as the sum over all vertices in A of the escape probability from the set A. So it's the probability that the quark starting from A never comes back to A. That's the first definition. I prefer the second one. And the second one involves the probability that we hit A when we start from far away. And I'm going to arrive at it using the first definition. So let me write what is the probability starting from X that HA is finite. So remember, we are in dimensions 3 and higher, and we want the probability starting from X that we ever hit the set A. So I'm going to write now what is called the last exit decomposition, which is a really useful formula. It's immediate to prove for random walk, but it turns out to be very useful. So if we want to hit A in finite time, in particular, it means that the last time that we hit A is going to be greater than or equal to 0. And so if we sum over all the possible last times that we are in A, then since we know that this is the last time, afterwards we are going to escape A forever. So this is going to be equal to the sum over all A in A of Gx minus A times the probability starting from A that we escape A. So this is called the last exit decomposition. So we get this Green's function because we sum over all the possible last times that we are in A, and so this is going to give us exactly how much time we spend at A, and then starting from A, since it's the last time, we will never come back. So we multiply by this probability. So if I now divide both sides by g of x, and I let x go to infinity, then this ratio is going to go to 1 because of the asymptotic. And so what we get is that the limit as x goes to infinity of this ratio, HA finite, divided by g of x, is going to converge to the sum of the escape probabilities, and this is exactly what we define to be the capacity of the set A. So this is the second definition of capacity, and it's the way I like to think about capacity as the renormalized probability that the random walks is the set A. And the third definition, which is probably the one that most people are familiar with, and it has the analog also in the continuum. Also, this has the analog for continuum capacity. You just replace the random walk by a Brownian motion, and the Green's function by the Green kernel for Brownian motion. So the third one, which is the variational characterization, says the following. So let me denote by EA of A what we call the equilibrium measure of A. So it's the probability time from A that we escape from A. So this is defined for points A in the set A. So this is called the equilibrium measure. And the normalized equilibrium measure is defined to be simply the equilibrium measure normalized by the capacity so that this becomes now a probability measure. So now if I consider the following set, so I take gx minus y, mu x, mu y, over all mu that are probability measures on A. So here I take the sum over all x and y in the set A. So we think of this as the energy of the measure mu. So the energy of the measure mu is the sum over all points in A of the Green's function times the measure. So now if I plug in E of A tilde, so this is a probability measure supported on A, and we use the definition of capacity and the last exit decomposition, it's immediate to see that this is given by 1 over the capacity of A. So plugging in the normalized equilibrium measure, we get that each energy is given by the inverse of the capacity. And then using the Cauchy-Schwarz inequality for the inner product defined by the Green's function, it's not hard to show that if we take the infimum of this set, this is actually going to be 1 over the capacity. So I took the inverse here, so it's going to be the capacity of the set A. So we have a measure a probability measure which achieves the infimum, and then for any other measure, we saw that it's at least this. So this is the final definition of capacity that I want to show. This is the variational characterization. So is it visible here if I write? Okay. So now that I have talked about random walk, so I explained what capacity is. So this gives some intuition of what one might expect for the case of percolation. But even though the 2-point function has the same expression as the Green's function for random walk, the critical percolation cluster doesn't look at all like the range of a random walk. And it turns out that, and this is a heuristic that has been around for a very long time, that critical percolation clusters in high dimensions resemble the range of a critical branching random walk in high dimensions. So let me explain what I mean now by a critical branching random walk. So criticality refers to the tree being a critical Galton-Watson tree. So in general, what is a branching random walk? It's a random walk which is not indexed by time, but instead it's indexed by a tree. So let me start by sampling TC. So TC is going to denote a critical Galton-Watson tree. So critical means that the mean of the offspring distribution is equal to 1, and we also assume that it has finite variance. So we have a Galton-Watson tree with offspring distribution of mean 1 and finite variance. So let me just draw the tree. And so on. So this is my tree TC. And now what I want is I want to embed this tree in ZD. So how am I going to do that? So let me call the root like this. And let's say that we send the root to the point X in ZD. Now, to every edge of the tree, we assign an independent random variable. So to every edge E of the tree, we assign a variable XE, which is uniform on the set of plus minus the basis vectors. So to every edge of the tree, we assign the increment of a single random walk on ZD. So let's say that we assign E1 here, minus E2, here E3, and so on. And now we want to define the branching random walk indexed by this tree. So we define, so S is going to be the branching random walk indexed by this tree. And so we set S of the root to be equal to X. And now for a vertex U in the tree, let's say the vertex is here, what we're going to do is we're going to take the geodesic from the root to this point, and to find the value of the walk at this vertex of the tree, we're going to add up the increments on the edges along this path. So this is going to be X plus the sum of xe for e in the path between the root and u. So this is the branching random walk indexed by the tree TC. And I'm going to denote by TCX. I'll indicate here the starting location of the root. This is going to be the range of S. So it's the set of points as u for u in the tree. And so if A is my finite set, what we are interested in here, if dimension is greater than or equal to 5, is what is the probability that the critical tree starting from X intersects the set A. That's the analogous question to the question for the random walk. And it turns out that if we divide this by the Green's function, the same Green's function as for the random walk, this is going to converge to something which Zhu called the branching capacity of the set A as X goes to infinity. So Zhu wrote his thesis in 2016 at UBC, and he showed that this limit exists, and he defined this to be the branching capacity of the set A. So one quick comment, why here we divide by the same Green's function as for the random walk. This is because the tree was taken to be critical, so the mean number of offspring is equal to 1. So if you try to calculate the local time for the tree, you will get exactly the same Green's function as for the random walk. So then the first question is this the same as the capacity of A, since we divide by the same quantity? And the answer is no, this is totally different to capacity. It's not the capacity of the set A. And Zhu obtained other expressions for the branching capacity, also in terms of escape probabilities. But I'm not going to state this result, but I'll state a limit result that he showed when you replace this tree TC here by an infinite tree. So what is this infinite tree? Let me write T infinity. The law of this tree T infinity is the law of the tree, of the critical tree condition on the tree surviving forever. So one has to make sense of this, and this was done by Kesten. But I don't want to go into detail in what this tree looks like. Okay, I can just say that this tree is basically a semi-infinite line, and of this infinite line, we have critical trees that are hanging off. So this is the description of this tree to infinity, and what Zhu showed is that if we now consider a branching random walk indexed by this tree, starting from X, the probability that this walk hits the set A, if we now divide by X to the 4 minus D, instead of 2 minus D here, times some appropriate constant CD, this is going to converge again to the branching capacity of A. Sorry, say that again? I divide by G of X, so it's 4 minus D. It's 1 over D minus 4, so. Because this probability is going to go to 0. The walk is transient. So that's the correct scaling. And so here, instead of 2 minus D, we get 4 minus D. So this is an indication that this branching capacity is not going to be the same as the what is called the Newtonian capacity. So the Newtonian capacity over here was defined with respect to the Green's function for random walk. So I'm going to put a gamma here and here. And what is G gamma? G gamma of X is defined to be 1 over X to the gamma. And so this was again done by Zhu. And so from here we see that the branching capacity should probably be given by a variational formula where we replace the gamma here by d minus 4 instead of d minus 2 for the Newtonian capacity. So this is what we expect. 2 years ago, with Amine and Bruno, we were able to show that this is indeed true, but we could prove it only up to constants. So this is upper bounded by one constant times the capacity d minus 4 of A, and lower bounded by constant times the d minus 4 capacity of A, where C1 and C2 are universal constants for all sets. So this is with Amine and Bruno. But we don't have a variational characterization only up to constants. So I've got 10 more minutes. Okay. Okay, thank you. Okay, so this is what I want to say about branching random walk, the results about the branching capacity. And now, as I said before, high-dimensional critical percolation clusters are expected to look like the range of critical branching random walk in high dimensions. And this is because the picture that is expected to hold for the critical cluster in high dimension is that it should be tree-like and it should contain very few cycles. And this is exactly the picture that one sees when one embeds a critical Galton-Watson tree into ZD. So now let me come back to percolation and let me state the results. So everything here is obtained with Amine and Bruno. So the first theorem says that if we look at the probability that X connects to the set A, and we divide by the two-point asymptotic, g of X, this limit exists, and we call this the P capacity of the set A. So this is our definition for capacity in this setting. So it's the rescale probability that X connects to the set A. To prove this result, this is not hard to show that this limit exists. But what we're interested in is to understand better this notion of capacity. So here again, we see the scaling X to the 2 minus D, just like for branching random walk and in the critical case for the critical tree. But we would like to also see this power 4 minus D. So what is the analogous object that one should consider in this case? So when we start with the critical tree, we consider the infinite tree, which was the critical tree condition to survive. And to make sense of this infinite tree, this has been done, and it's not particularly hard. But to make sense of the infinite cluster, when you take a critical cluster and you condition it to survive forever, this is a much, much harder question. So let me define what is called the IIC. So this is called the incipient infinite cluster. So we start with the cluster of 0 at criticality. We know we are in the setup where we have the two-point function, and so we know that this cluster is going to be finite with probability 1. And we want to condition, say that 0 is connected to a faraway point, and we want to send this faraway point to infinity, and would like to see what object we obtain in the limit. So this was done. As I said, this is much, much harder to do than for the tree, and this was first done by van der Hofstad and Antal-Yarai. So they had already the results on the two-point function, but they had to redo Lace expansion to define this IIC measure when you condition 0 to be connected to a faraway point and you send this point to infinity. So that was the first construction of the IIC, but they could only prove this existence when you condition that 0 is connected to a faraway point. And with their techniques, they could not get it when you condition that 0 is connected, say, to a faraway ball. But there is a recent preprint from February 2025 by Chatterjee, Chinmay, Hanson, and Soso. It's a very beautiful paper from 2025. They built upon the work of Kozma and Achmias, and they actually show that any definition of the IIC gives rise to the same limit. So it doesn't matter if you condition 0 to be connected to X or to a faraway set or to a faraway set avoiding other obstacles, you always get the same limit. So I'm going to denote the IIC of X like this, C infinity of X. And so what we could prove is that this limit, if we scale by X to the 4 minus D, sorry, there's no limit here, it again gives us the P capacity. So the probability that C infinity of X intersects A divided by X to the 4 minus D is up to constants the P capacity of A. And again, this is valid when X goes to infinity. So here we cannot prove that this limit exists. And actually, even when A is just 1 point, this is not known that this limit exists. But what we're able to show is that the lim sup and the lim inf are up to constants given by this notion of P capacity. Okay, so now the last question, the third question is, can we characterize P capacity? Can we show that it's equivalent to branching capacity or in particular to the D-4 capacity? And this is what one should expect when we see the power 4 minus D and by the well-known analogy between the two objects. So we were not able to show that P capacity of A is the same as D-4 capacity, but what we're able to show, and I would like to show you the proof of this, is that the P capacity of A is always at least some constant times the D-4 capacity. So we're able to show a lower bound in terms of the D-4 capacity, but the upper bound is still missing. So, but already with this lower bound, we can get some interesting results, even though, so let me say, I think I will have time to present the proof of this. So what we like about this statement, so the proof, I can just explain it in 3 minutes, and it uses a really nice idea by Fitzsimmons and Salisbury, and it also appeared in another paper by Salisbury, and they worked in the setup of random walks. So, and this idea, as far as we know, it has not been used before in percolation. So this is thinking of the percolation cluster in terms of a random walk. So why is this useful, this lower bound? So what it says is that what we actually show is that the probability that X connects to a set A is at least G of X. This is for the critical cluster times the D-4 capacity of A. This is what we show, and then knowing that the limit exists, we get exactly that P capacity is at least the D-4 capacity, and this is valid as long as X is larger than, say, 10 times the diameter of A. So why is this useful? So it is useful because if A is a sparse set, so if the intersection of A with a ball of radius r is much smaller than the volume of the ball, I don't want to make it precise, if you're interested I can write, then the capacity D-4 of A is at least the size of A. So this is really easy to show under this condition on A, just using the variational formula. It's really easy to show that the capacity is going to be at least the size of A. So what this is saying now is that for such A, for such sparse A, the probability that X is connected to A is up to constants G of X times the size of A. So the lower bound comes from this, and the upper bound is immediate using simply a union bound. And so using this asymptotic for such sets A has enabled us to simplify previous proofs and to prove other results. So maybe in the last few minutes, I'm going to present the proof of this lower bound. So proof of lower bound. So we want to show that the probability that x connects to A is at least g of x times the d minus 4 capacity of A. So what is the idea of Fitzsimmons and Salisbury? Let's take mu to be a probability measure on the set A. And what we're going to do is we're going to define our random variable z, which is equal to the sum over all A in A of mu of A times the indicator that A communicates with X. So of course, if X communicates with the set A, then this probability is at least the probability that Z is positive. If Z is positive, of course, X communicates with A. And now I'm just going to use the Paley-Zygmunt inequality, and lower bound is by the expectation of Z squared divided by the second moment of Z. So the whole proof boils down to calculating first and second moments of Z. So now let's first look at the first moment. The expectation of Z is going to be the sum of mu of A times g of A minus X, but I'm going to take X to be far away, so g of A minus X is essentially the same as g of X. So the expectation of Z is going to be up to constants g of X times the sum of mu of A, which is a probability measure, and so it is equal to 1. And now, I'll just write over here. And now we just need to calculate the second moment of Z, and then we are done. So let me write the second moment. So the second moment of Z is given by the sum over all A and B in A of mu of A times mu of B times the probability that A is connected to both X and B. So we just need to upper bound this probability. Now, if we have 3 points, A, B, and X, and they're all connected to each other, so let's take A and B not to be equal, then there must exist some point Z so that these 3 events use disjoint sets of edges. So this probability, I'm going to upper bound it by the sum over all Z of the probability that A connects to Z disjointly from Z connecting to B disjointly from Z connecting to X. So I just want these paths to use disjoint sets of edges. Now, if I condition on these 2 events, and I want the probability that A connects to Z, so I'm asking for A to connect to Z, but without using the edges that have already been used. So intuitively, and this can be proved rigorously using what is called the BK inequality, but intuitively, this probability should be smaller than the probability that A connects to Z. And then similarly for the other 2 events. And so what we get by the BK inequality is that this sum, this probability, is upper bounded by the product of these 3 green kernels. And now, if we take X to be far away, this will be of order g of X. And so then what we get here is the sum over all Z. So this will be g of X. And this will be the sum over all Z, GA minus Z times GZ minus B, which is nothing else but the convolution of G with itself. And G is X to the 2 minus D. And so what is this? This is of order GD minus 4 of A minus B. So what we showed is that the second moment of z is upper bounded by g of x times the sum over all a, b in A, mu of A, mu of B, times gd minus 4 of A minus B. And so if we plug this into the Paley-Zikmund inequality, this is going to give us exactly the lower bound that I wrote over here. And so this completes the proof, and that's the end of my talk.
Thanks a lot. Questions? I see 2 hands.
So we are working as long as the 2-point function estimate holds. So if we have this, then, so this expect up to dimension 7. And so we work under this assumption.
There's a question somewhere, I forgot.
A naive question. So 0, 1 is the definition of a peak capacity, right?
Yes.
So, if I didn't misunderstand something, whenever you have a bound like of the 2-point function, maybe not the exponent is not d minus 2, is another exponent. People play that game these days, no? Then this proof should work for the analogous definitions of the capacities, right?
I think so, probably yes.
Okay.
Other questions? So just to make sure, so it was already asked, but I'm not sure about this. So theorem 1 and 2, they hold in which dimension? So when the lace expansion works? Or
Yes.
Okay.
When we have the 2-point estimate, yes.
Whenever you have input from...
Yes.
Okay, so if there is no other questions, thanks again.